Hello, this is the last time we're going to be updating our packet, and so we're going to be adding two more equations to our packet here, and they're going to be equations that you used on your Snell's Law PhET Lab and equations that came from your Chapter 17, Section 1 homework. So here we go. I'm actually pulled up the homework here. So this is what Chapter 17, Section 1 looked like. There was an equation right here for the speed of light in a material. So we have talked about before that the speed of a wave actually depends on the medium that it travels through. For light actually slows down when it enters in a new medium that is a solid or a liquid, whereas whereas sound actually speeds up when it goes into a liquid or a solid. So sound actually goes faster in water and even faster in a solid. But light does the opposite. It slows down because those particles are more densely packed together. So what you're going to do with this equation is we are going to write it on the front of our packet, but I just want to point out we already know what V is. That's just speed or velocity. And then c is the speed of light in a vacuum, which we also know, which is 3 times 10 to the 8th meters per second. But the only new variable in this equation is lowercase n. N is the index of refraction of a material, and you've also been using that in Snell's law, which we'll talk about in just a second. So let's go ahead and write this down in our packet right here. Let me get rid of this stuff so it's out of the way. There we go. Okay, so at the bottom of our packet, we have room for two more. We're going to do speed of light in materials. And remember, the equation, which we were just looking at, is V is equal to C over N. Now this looks really similar to the general speed equation, and the way that you can tell whether or not you're going to be using this equation or this equation is what you're given and what you need to find, okay? The only new variable that we're going to write over here is n. N is the index of refraction, and it actually does not have a unit. It is unitless. It's just a number. So it's going to be kind of like a constant number. It's based off of what the material is made of. Down below, this table right here is also in the very back of your packet. You'll see that there are different substances, and they're listed with the different indices of refraction. It starts with the slowest light can go, which is in a diamond. A diamond is the most dense substance, the hardest substance, and so that is going to have the highest index of refraction, which is 2.42. So light travels very slowly through a diamond, and that's actually one of the ways you can tell if you have a real diamond or not. But as we go lower on the table, you're going to see that different types of glass or quartz or ice, different liquids like benzene, ethyl alcohol, water, things like that, and then different gases, carbon dioxide, air. So all of these have different indices of refraction, and that means that light is going to travel at different speeds through those different materials. All right, let's keep scrolling down and talk about Snell's law. Now, Snell's law, they give this example right here, but I'm going to think of a real life example, especially for those of you who drive. If you've ever driven on a dry, asphalt road, and then maybe hit a big puddle of water, that's pretty common, or it was just snowing, so you're driving on the dry road and then you hit a patch of ice or something like that. Whenever you're driving and you hit a patch of some other sort of material, let's say some sort of water, you're going to feel a pull on the tires, and incidentally a pull on the wheel itself because you're holding onto the wheel. The reason why you feel a pull is because you're going from dry asphalt to, let's say, a patch of ice on the road, and those have different friction coefficients of friction. So if they're going to be different friction-wise, the tires are actually going to pull differently when they're touching those different materials. The same thing happens with waves. When waves enter a new medium, it's kind of like different friction of the particles that the wave has to travel through. And so sometimes your tires are going to travel pretty slow on asphalt compared to ice, because ice has very low friction. And so you're going to feel your tires kind of pull to one side or the other. And the best way to handle something like this is to actually just hold onto the wheel and keep the wheel straight. Okay, but for our purposes of talking about light waves, this is Snell's law. Basically, light is traveling from one material. So let's say this green material up above is where the light ray is coming from. And when it hits this boundary, it can do one of three things. It can reflect, it can be absorbed, or it can be transmitted. Well, we're going to focus on the transmitted part. That transmitted light ray is called a refracted ray. And notice how the angle actually changes. If the index of refraction, this brown material, is higher than the index of refraction of this green material, which is what this is saying right here, N2 is greater than N1. If this is a thicker material, a more densely packed material, the light ray is going to bend towards this thing called the normal. It's we'll talk about what the normal is in just a second, but it's going to bend towards the normal because it's actually going to slow down. So when the light ray enters from a medium of lower index of refraction to a higher index of refraction, that ray is going to bend. Now, the normal is actually a perpendicular imaginary line. That's why it's dotted. Okay, the normal is actually something we use to represent where that light ray is entering. And so we use the normal, which is perpendicular to the surface right here, to measure the angle from. Notice we're not measuring the angle from the barrier itself, because the barrier may not be smooth. This could be bumpy, it could be wavy, it could be mixed because it's one type of gas mixing with another, something like that, okay? So we're actually going to use this fake dashed line, which is perpendicular to right where the light ray enters, to measure our angles of incidence and refraction. The incident angle is meaning the incoming angle. So incidence means incoming, and that's why we label it with a 1. So this is theta. This is the Greek letter theta. Theta sub 1 is our incident angle. N sub 1 is our incident index of refraction. So this is our very first material that the light ray is traveling through, and then the light ray bends when it enters in the second material, and that's going to have N sub 2, our index of refraction, and this is going to be our angle of refraction, theta sub 2. So here comes the big equation right here. N sub 1 sine theta 1 is equal to N sub 2 sine of theta 2. Sine is a trig function. Now, maybe you haven't gotten to trig yet in math, which is totally fine, but I'm going to show you where these buttons exist on your calculator after we write this equation on the bottom of our packet. So let's go over to our packet really quick. Here we go. The packet, right at the bottom, we're going to write Snell's law, and that's going to be the equation we just looked at, N sub 1 times the sine of theta. That's how you draw theta. It's like a big 0 or a big circle with like a little hat across the top, sub 1. And that's going to be equal to N sub 2 sine of theta sub 2. So these are all multiplying. N sub 1 is multiplying by sine of theta 1. N sub 2 is multiplying by sine of theta 2. So most of the time we're going to divide if we're trying to move things around. But there is one special thing I do want to teach you in just a second. All right, we do have N as our index of refraction. So obviously 1 and 2 are just the different materials. But sine of theta, there's theta, and I'm going to write the name because it's a Greek letter, theta. That's going to be our angle. Not angel, angle, okay? And that's going to be measured in degrees. So you do need to make sure that your calculator is in degrees and not radians, especially for those of you who are in calculus and using radians and stuff already. So we're going to have our angle in degrees. Okay, now here's where these trig functions are, and I do not want you to feel overwhelmed by using trig functions. They're really not difficult at all. Okay, it's just like any other function, like x squared or square root or any of those things. Our trig functions here on the class calculators are right here, and you're really only going to be using sine. But I do want to point out, and we can do an example from the packet if you like, but you're going to need to do something called inverse sine, and if you can see it right above my fingernail right there of my pointer finger, it's sine with a -1 exponent up there. Sine to the -1 power is the inverse sine, and that's actually how you find theta when you're trying to find the angle. So when you guys are working on your PhET lab, we're actually going to be using the inverse sine. Okay, if you have any questions for the Snell's Law examples from the packet, please let Miss Davis know, and she can tell me which ones to go over. That is all of the equations for the entire packet, and so I'm going to go ahead and stop it right there.